Okay, this is going to be a crash course in logic for the math team members, especially those of you who never studied logic before. So, logic is the science of reasoning, and the building blocks of logic are things called statements. So, easy statements would be things like x equals 3 or x greater than 2, things like that. And normally we label statements with lowercase letters starting with P. So like this would be statement P, this would be statement Q. So the first thing we need to do is learn how to negate statements. Like if you have a simple statement like this, P, then the negation of P, or we simply say not P, is x is not equal to 3. Very simple. If you have the statement x is greater than 2, then the negation of that statement, or not Q, is x is less than or equal to 2. So it's very simple to negate simple statements, okay? But what about if you have more complicated statements? For example, the first one is called the universal statement. So a universal statement looks like this. For all real numbers x and y, comma, x plus y squared is equal to x squared plus y squared. Okay, that's called a universal statement because of the first two words, for all. We're talking about all real numbers. And we can symbolize this statement like this. For all x and y, which are elements of the real numbers, x plus y quantity squared is equal to x squared plus y squared. That's how we symbolize it. And the kind of logic that we're studying is called two-valued logic, where every statement is either going to be true or false. So you can see that this statement here is false, right? Because we know that x plus y quantity squared is x squared plus 2xy plus y squared. Okay. Another kind of statement would be called the existential statement. Existential. An existential statement looks like this. There exists in integers a and b, such that pi equals a over b. See, and we call it existential because look at the first word, two words, there exist. There exist in mathematics means there's at least one. So there's at least one pair of integers a and b such that pi equals a over b. No, this is a false statement, right? Because we know pi is an irrational number. And we can also symbolize this statement like this. There exist a and b, which are elements of the integers, such that pi equals a over b. So every universal statement has the same form. For all box, comma, oval. It's always the same form. And same thing with existential statement. There exists box such that oval. So what about negating these statements? So if we call this statement P, let's say P is a universal statement, then the negation of P, or not P, would be there exists box such that not oval. And same thing over here. If Q was an existential statement, then the negation of it would be for all box, comma, not oval. So if we apply it to this, let's say this is statement R then. R is this universal statement there. Then the negation of it would be there exist real numbers x and y such that, and if this is the oval, then not oval. So it would go x plus y squared is not equal to x squared plus y squared. And that's how you negate a universal statement. So it really doesn't matter what the words are, you just look at the form. So same thing over here. Let's say this is statement S. There exist integers a and b such that pi equals a over b. The negation of it, let's do it over here. The negation of it would be for all integers a and b, comma, and if you think of that as oval, then not oval. Oval, pi is not equal to a over b. So if you have a statement and we already figured out it's false, then by default its negation must be true. Because that's what negation is. Negation is like the opposite of it. Same thing over here. If S is this statement here, which we already said is false, then its negation has to be true. So that's how you negate universal and existential statements. It's quite easy, just look at the form. Okay, let's look at some examples. What if somebody said all prime numbers are odd, which of course we know is false. So let's call this statement P. What would be the negation of that? So all means like for all, right? That's a universal statement. So we know the negation is going to be existential. So some prime numbers are not odd, right? You just follow the form. Okay, let's look at another example. Q. What about some? So some means at least one, which is existential, right? Some prime numbers are even, which of course we know is true, right? Because 2 is the smallest prime number, which is even. Then how do you negate that? Well, the negation of existential is universal. So all prime numbers are not even. But it's better to write odd, yeah? So that's how you negate that. And then what about something like this? Let's just do one more. No prime numbers are even. What would be the negation of that statement? Like if somebody said no prime numbers are even, what would it take to prove that person wrong? Some, at least one, some prime numbers are even. And there you go. So that's how you negate statements. So that's the beginning of logic. You got to learn how to negate statements. Okay, next thing on the list, truth tables. Okay, let's look at negation. When you have a statement P, there's only two possibilities. It's either true or false. So the negation of it, well, if the original statement is true, its negation must be false. If the original statement is false, the negation must be true. And there you go. That's an example. That's the easiest truth table there is for negation. A truth table basically shows all the different possibilities of a statement. Okay, now what happens when there's two statements though? P and Q, like this. Then there's four possibilities. And the standard way of making the truth table would be like this. True, true, false, false. True, false for Q. And there you got all four possibilities. Now, one way you can connect these two statements is using or disjunction. So if you see this is the disjunction of P and Q. Or we simply say P or Q. Now that kind of looks like the union symbol, right? And just to review union and intersection, let's do a quick review of sets. If set A contains the elements 1, 2, and 3, and set B contains the elements 2, 3, and 4, then what is A union B? Union means if you throw everything in A in a box, then throw everything B in B in a box. What's in the box? 1, 2, 3, 4. Right? That's union. That's everything that's there. And intersection would be what elements are common to both. And of course, that would just be 2 and 3. Anyway, this or sign looks very similar to this union. And that's because they mean the same thing. Except that you use the union symbol when you're connecting two sets. You use this symbol or to connect two statements. But they mean the same thing. Just like over here. This negation sign is like the negative sign. Except numbers are negative, statements are negated. A subtle difference, but it is a difference. Anyway, this is the or statement or disjunction. The or statement is true if at least one of the two components is true. So you look at this. Is at least one of them true? Yes, so it's true. Is at least one of them true? Yes, so it's true. Is at least one of them true? Yes, so it's true. Is at least one of them true? No, so it's false. That's how the or statement works. Just like union up here. It's the same thing. except you're doing it with two statements. Okay, next one is this. It looks like this is intersection. Hello, gosh, getting old. Intersection. That looks like intersection. It means the same thing, except you use this when you connect two statements. You use this when you, what am I saying? This when you connect two sets. This when you connect two statements. Okay, the AND statement is true when both components are true. So are both components true? Yes, so it's true. Are both components true? No. Are both components true? No. Are both components true? No. And that's how the AND statement or conjunction works. So this is disjunction. This is all in your notes now. Yeah, you got to remember these terms. AND is conjunction. Okay, the next one is called the conditional statement. Now, before I make the truth table for this, let's do some review from geometry. If you have a conditional statement, which is P implies Q, or if P then Q. In fact, there's lots of ways of saying it. The most common ways would be if P then Q, or P implies Q, but there's also some other ones. Q if P. P only if Q. P is a sufficient condition for Q. Q is a necessary condition for P. They all mean the same thing, that right there. That's called a conditional statement. But if you have a conditional statement, you can form these other statements. First one is called the converse. The converse of P implies Q is Q implies P. You can also form the inverse. The inverse of P implies Q would be not P implies not Q. And then the most important one, the contrapositive. I'm sure you remember this from geometry. The contrapositive of P implies Q is not Q implies not P. So if you're given a conditional statement, you can form other statements from it. Okay, so this is called the conditional. Anyway, the truth table for the conditional statement looks like this. It's true, false, true, true. Notice the only time that it's false is when the first one is true and the second one is false. Okay? So that's the only time the conditional statement is false, is when the first one is true and the second one is false, and it's true in all other cases. And then the last one you need to know is called the biconditional statement. Biconditional. Notice how the arrow points both ways. Biconditional means if P then Q and if Q then P. That's what it means. You can go either direction. Whereas in the conditional, it means if P then Q. If two parallel lines are cut by a third line, then the alternate interior angles are equal. But this one you can do either way. If P then Q and if Q then P. The truth table looks like this. Notice that the biconditional statement is true when the two components are the same, either both true or both false, and if they're different, then it's false. So these are the basic truth tables that you need to know. Now, what do you do with truth tables? Well, we prove a lot of things with truth tables. So let's look at some things. And these are all in your notes, but of course, ultimately, it has to be committed to memory. So suppose you have two statements. Should have left it on the board. P is true, true, false, false. True, false, true, false. Okay, these are the four possibilities. Now I'm going to put the conditional statement here. P implies Q. And we already know it's true, false, true, true, right? The only time it's false is when the first one is true and the second one is false. Let's make a truth table for not Q implies not P, which is the contrapositive of that. Okay, well, if Q is true, false, not Q, the negation of Q would be the opposite of that, which would be false, true, true. If P is true, false, then not P is going to be the opposite of that. False, true, true. And then how does conditional work? The only time it's false is when the first one is true and the second one is false. That's right here. And it's true in all the other cases. So this line here would represent this statement there. And what do you notice? Hey, it's exactly the same as the conditional statement. When two statements have exactly the same truth table, we say that those statements are logically equivalent. So P implies Q is logically equivalent to not Q implies not P, which is the contrapositive. Which means the contrapositive of a conditional statement means exactly the same thing as a conditional statement. Exactly the same thing. That's because their truth tables are the same. And notice how this symbol for logically equivalent kind of reminds you of the equal sign? Yeah, it means the same thing, except only numbers can be equal. Statements are logically equivalent. Okay, let's make a truth table for something else. How about not P or Q? Okay, well, if P is true, true, false, false, not P would be false, false, true, true. And Q we know is true, false, true, false. Okay, but we're going to connect them with OR. The OR statement is true when at least one of them is true. So you look at the two. Is at least one of them true? Yes. Is at least one of them true? No. Is at least one of them true? Yes. Is at least one of them true? Yes. So this represents that statement there. And lo and behold, it's the same as the conditional. So the conditional statement is also logically equivalent to an OR statement, which is not P or Q. And this is going to be very important later. To convert a conditional to an OR statement or to conditional, the pattern is you negate the first one and you leave the second one alone. That's how you do it. Okay, let's do some more. Okay, let's put the okay, let's do truth table. Make a truth table for this, not P or Q. And then let's also make a truth table for not P and not Q. You can probably guess what's going to happen. Okay, P or Q. Remember, P or Q, the OR statement is true when at least one of them is true. So you look at these two. True, 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 false. So it's true, 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 false. But then you're going to negate it, so you're going to get false, 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 true. So this column represents this statement there. Okay, now what about not P and not Q? Well, P is true, true, false, false. Not P is going to be false, false, true, true. And if Q is true, false, true, false, not Q is going to be false, true, false, true. And how does the AND statement work? The AND statement is true when both components are true. So are both of them true? No. Are both of them true? No. Are both of them true? No. Are both of them true? Yes. So this column represents this statement. And if you look at these two, hey, they're the same. They have exactly the same truth table, which means they are logically equivalent. So not P or Q is logically equivalent to not P and not Q. This is called De Morgan's law. Some books call it the law of distribution because it reminds you of the distributive property. So you can distribute a negation sign to an OR statement, but it's going to be an AND statement. Right? You can distribute the negation sign, but you got to change OR to AND. And I'm not going to do it here, but if you make the truth tables, you will also find that you can distribute a negation sign to an AND statement by doing this, not P or not Q. Just change the AND to OR. And it reminds me of the things we learned in logic. Yeah, it's the same things. A union B complement is equal to A complement intersect B complement. That's exactly the same thing as this, except you're just doing it with sets. Complement is like negation. A intersect B, intersect rounded, complement is equal to A complement union B complement. That's exactly the same thing as this, except these are two statements, these are two sets. See how everything fits together? So truth tables are important because we need to know what statements are logically equivalent to which statements. If you made a truth table for something that comes out true every single time, we call that a tautology. So a tautology is a statement that comes out true every single time when you make a truth table. A statement that comes out false every single time is called a contradiction. So these are just terms that you have to know. Now what would happen if you had to make a truth table for like 3 statements? P, Q, and R. Then there would be 8 possibilities. And the truth table would look like this. True, 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 true. So this is the standard way of doing it so that we get all 8 possibilities. True, 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 false, 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 false for P. And then Q would alternate by 2s. True, true, false, false. true, true, false, false. And then the one on the furthest right would always alternate by ones. True, false, true, false, true, false, true, false. And then you would use the same thing like if you had 4 statements. The one on the right would alternate by ones. Then if you go to the left, the next one in alternates by 2s, then by 4s, then by 8s, by 16s, and so forth and so forth. Now for Math League, you are not required to make a truth table for an answer. Well, an answer cannot be a truth table. However, you might have to do a truth table in a problem to get the answer. Okay, so now that we got that down, the next order of business is arguments. There are 2 basic arguments in logic. This is the first one. P implies Q. P, therefore Q. This is called an argument. These 2 statements up here are called the premises. This is called the conclusion. An argument is said to be valid if, whenever the premises are true, the conclusion is true as well. That's called a valid argument. So if this is true and this is true, if that is true, we call this a valid argument. Okay, now, how do you determine if an argument is valid? Well, you make a truth table like this. So here's the first premise, like that. Then here's the second premise. I'll put a double bar just to separate it, and that's the conclusion. Simply make a truth table for this. So the truth table for P implies Q, I hope we remember, is true, false, true, true. P is always true, true, false, false, right, when you just have 2 statements, and Q is always going to be true, false, true, false. Okay, so here are the 2 premises. Where in this truth table are both premises true? In line 1, and that's it. Now in this one, they're both true only in line 1, but sometimes when you make a truth table, both premises will be true in many lines, so you have to look at all the lines. And whenever they're both true, does the conclusion come out true? Yes, so that's how we determine that this is a valid argument. Okay, so what if you had, okay, let's just say, what if this was also true there? So when both premises are true, if the conclusion comes out false just one time, then this is an invalid argument. So whenever the premises are true, the conclusion has to be true every single time. Not just once, every single time. Okay? And that's how you tell if an argument is valid. Okay, so a way to think about a valid argument would be like, okay, if you do your homework, then I'll pay you $5. You do your homework. What would be a logical conclusion? You're going to get $5. Right? Makes sense. See, you don't want to have to rely on the meaning of the words. See, that's the thing about logic. So that's why we symbolize. So it doesn't matter what the words are. If we symbolize, then we can come up with a valid conclusion no matter what. Okay, another valid argument is this one. Oh, by the way, this is called modus ponens, method of placement. And the next one is called the law of syllogism, which is this. P implies Q, Q implies R. Therefore, what can I conclude? P implies R, right? That makes sense. Sometimes some books call this the law of transitivity because it reminds them of the transitive property of equality, you know, which is this. If A equals B and B equals C, then A equals C. Right? Kind of reminds you of that. Okay, anyway, so one of the most important things in logic is if you have a bunch of premises, you have to be able to come up with a logical conclusion. So we're going to use these 2 to figure it out. Okay, let's look at some easy ones. P implies Q, Q implies R, R implies S, S implies T. P, therefore what? If these 5 premises are true, what would be a logical conclusion? Well, if you look at these 4 right here, P implies Q, Q implies R, R implies S, S implies T, we can use the law of syllogism to deduce that P implies T. But then now P, so by modus ponens, if gorilla implies banana, gorilla, therefore banana. See, so basically we just use these 2 to deduce a logical conclusion. Okay, let's look at some more. P implies Q, not Q. Therefore what? if these two are true, what would be a logical conclusion? Well, what did we learn? A conditional statement is logically equivalent to its contrapositive. So if I replace this with its contrapositive, notice that we have modus ponens now. Gorilla implies banana. Gorilla, therefore banana. Also, Mr. Park, we need to know which statements are logically equivalent. Yes. Yes, you do. You have to know them all. That's why they're in the notes. Okay, let's look at a few more. How about this? P or Q, not P. Therefore what? If these two statements are true, what would be a logical conclusion? Well, I can replace an or statement with a conditional. Remember how? You negate the first, leave the second one alone, right? That was one of our logically equivalent things. And then now look how easy this is. Gorilla implies banana. Gorilla, therefore banana. That's modus ponens again. Okay, what about this? Not P and Q. P, therefore what? Well, what's logically equivalent to that? Well, you can distribute the negation sign using De Morgan's law. So that would be not P or not Q. But then we can replace that with a conditional by negating the first and leaving the second alone. So look at that, we got modus ponens. Gorilla implies banana, gorilla, therefore banana. Okay? So those are some easy examples, and in this event, you're not going to get anything too complicated. So I think that's it for logic. Those are the building, but yeah, I can't think of anything else. So hopefully that's a good crash course in logic. If you need help, come see me. Or else castration!